Welcome everyone. Today we are diving into the sample selection procedure, a critical topic in official statistics. Imagine you are cooking a massive pot of soup. You do not need to drink the whole pot to know if it needs more salt. You just taste one well-stirred spoonful. In statistics, this procedure is our mathematical way of stirring the pot, ensuring our small sample perfectly reflects the larger population. Let us explore how this works. Now that we understand the goal is to taste the soup, let us look at how we actually scoop it. A sample selection procedure is a strict step-by-step mathematical method used to pick a small group from a larger population. Why do we need such a rigid procedure? Because humans are naturally biased. If a teacher just picks students sitting in the front row, the sample is flawed and unrepresentative. A proper mathematical procedure eliminates this human bias entirely, guaranteeing that every single item or person has a known, fair chance of being chosen. Before we can randomly pick anyone, we need to know exactly who is in our target population. This brings us to the concept of the sampling frame. Think of the sampling frame as the master list, much like a school's official attendance register. It is the absolute foundation of our entire survey. If a student's name is missing from that register, they have absolutely zero chance of winning a random prize draw. The mathematical selection procedure can only be as good as the list it uses. A perfect procedure on a bad list still yields bad results. Unfortunately, in the real world, perfect lists almost never exist. This leads to sampling frame errors, which can ruin our fairness before we even begin picking names. There are three main culprits to watch out for. First is undercoverage, where people are completely left off the list, like a phone book missing mobile users. Second is duplicate listings, where someone appears twice, unfairly doubling their chances of being picked. Finally, outdated records include people who have moved away or passed away. A broken frame guarantees a biased, untrustworthy sample, no matter how good your math is. Let us visualize these errors. On the screen, the left circle represents everyone who should be in our survey, the true target population. The right circle is our actual sampling frame, the list we have. Notice the overlap? That is our valid frame. But look at the red area on the left. Those blue figures are undercoverage. They exist in reality but are missing from our list. On the right, you see pairs of green figures. Those are duplicate listings, giving those individuals an unfair advantage. So, how do we actually pick names from our valid frame fairly? Historically, statisticians used the lottery method, literally drawing paper slips from a mixed bowl. But for 1 million people, that is physically impossible. They then invented random number tables, thick printed books of machine-generated digits. Today, virtually all professional surveys use computer-generated random numbers. Software like Excel or Python uses complex formulas called pseudo-random number generators. By setting a digital seed, we ensure the computer's lightning-fast random choices can be perfectly repeated and verified by other researchers, completely eliminating human bias. The most fundamental computer selection method we use is called simple random sampling without replacement. The key phrase to focus on here is without replacement. It simply means that once a person or item is picked for the sample, they are permanently removed from the available pool. They cannot be picked a second time. This prevents us from surveying the exact same person twice, which would be a waste of resources, and ensures our final sample is as diverse and informative as possible, perfectly reflecting the larger population. This brings us to the mathematical heart of fairness. In simple random sampling without replacement, what is the exact chance that any specific person makes it into the final sample? The formula is beautifully simple. Pi equals n divided by n. Here, Pi represents the total probability of inclusion for any specific unit. Lowercase n is our desired sample size, and uppercase N is the total population size. Notice the relationship here. If the total population n increases while your sample size stays the same, your individual chance of being picked shrinks proportionally. It is a perfect mathematical balance. Before we prove why that formula works, let us see this selection procedure in action with a concrete example. Imagine a small village with a population of 800 farmers. The government wants to test a new fertilizer and needs a sample of exactly 5 farmers. First, we assign every single farmer a unique ID number from 1 to 800. Then, we ask the computer to generate 5 random integers. The computer spits out a raw sequence: 42, 715, 42, 108, 550, and 213. Notice anything wrong with this raw list? You probably spotted the issue immediately. The number 42 appears twice in our raw sequence. Because our strict rule is sampling without replacement, a single farmer cannot be selected to toss the fertilizer twice. The software algorithm automatically detects and discards the second 42. To ensure we still get exactly 5 unique farmers for our study, it pulls the next random number in the sequence, which is 213. Our final valid sample consists of IDs 42, 715, 108, 550, and 213. This is exactly how modern surveys handle the without replacement rule seamlessly. Now that we have used the procedure in a real-world scenario, let us understand exactly where the inclusion formula comes from conceptually. We want to mathematically prove that the total chance of being picked is n over capital N. To do this, let us track a specific person in our population. Let us call him John. What is the probability that John is selected on the very first draw of the lottery? It is simply 1 over capital N. Why? Because there is exactly one John in the population and there are n total people available in the pool. This simple fraction is our starting point for the entire proof. What if John misses the first draw but gets lucky on the second draw? We must calculate the probability of this exact sequence. The chance he fails the first draw is n minus 1 divided by n. On the second draw, there is still exactly one John waiting to be picked, but there are only n minus 1 people left in the pool because one person was already removed. When we multiply these two probabilities together, the n minus 1 terms in the numerator and denominator cancel out perfectly. The result is beautiful and surprising. The probability of being picked on the second draw is exactly 1 over n, which is the exact same probability as the first draw. By mathematical induction, we can extend this logic to every single draw. John's chance of being picked on any specific draw, whether it is the third, fourth, or final draw, is always exactly 1 over n. Because he can only be picked on the first, or the second, or the third draw, these are mutually exclusive events in probability. Therefore, we simply add these individual probabilities together. We are adding 1 over n exactly n times, representing our total number of n draws. This addition gives us our final elegant formula, n over n. We have successfully proven that every single person has the exact same fair chance of inclusion. So we have proven that our mathematical selection is perfectly fair. But this brings us to an important question. What happens when reality interferes? The elegant formula we just derived assumes a flawless sampling frame. If the list is broken, the math breaks right along with it. Missing records will drop a person's chance of selection to absolute zero, silencing them completely. Meanwhile, duplicate records will unfairly multiply a person's chances, giving them a louder voice than others. This completely destroys the integrity of the entire survey, making the results untrustworthy. Before we move on, let us see this distortion with a concrete example. A college wants to survey 100 students about cafeteria food out of a true population of 2,000 students.
However, their email list is outdated. It is missing 200 newly admitted students and contains 100 duplicate emails. First, we must find the size of this broken list. We take the 2000 true students, subtract the 200 missing students, and add the 100 duplicate records. Our flawed frame size is exactly 1900 entries. This is the list the computer will actually use.
Now, what is the probability that a newly admitted student is selected? Because they are completely missing from the sampling frame, their chance of being picked is exactly zero. They have absolutely no voice in the survey. What about a normal student with exactly one correct email on the list? Using our inclusion formula, their chance is the sample size, 100, divided by the flawed frame size, 1900. This simplifies to 1 over 19. This 1 over 19 is the baseline fair probability for this specific flawed survey. Finally, what about the student who accidentally has two emails on the list? We must calculate the probability that at least one of their two emails is chosen. We take 1 and subtract the probability that neither email is picked, using combinations of the remaining emails. The math reveals their chance is approximately 200 over 1900, which simplifies to 2 over 19. This is twice the probability of a normal student. This proves mathematically how frame errors completely destroy the fairness of our sample selection procedure, giving some people an unfair advantage. We have covered a lot of ground today. Let us review the key takeaways. First, sample selection is not just picking at random. It is a strict mathematical protocol designed to eliminate human bias. Second, simple random sampling without replacement guarantees every unit an equal inclusion probability of n over n. But most importantly, even the best computer algorithms are useless if your sampling frame is flawed. Mastering both the math and the list quality is the only way to guarantee a truly representative sample.